There are many applications where we want to approximate the shape of a function with a different function. That may sound unusual, but it's actually pretty costly to work with a lot of different, mainly transcendental functions like trig functions, exponential functions. There's just a lot more to compute, and the computations are a little bit more difficult. I think we take it for granted. If you take the sine of pi, well, that's zero. That's a common angle. But what about the sine of, say, 2.5? And how do you approximate that? Well, your calculator does some work in computing that, but what does it do? Well, one way that it could calculate that is to use what's known as a Taylor series approximation. And the idea here is that if you can replace a more complex function like a trig function with something simpler like approximating with a polynomial, then you could simplify the derivatives, right? Because taking derivatives of polynomials is just applying the power rule. Remember, polynomials are terms like linear, cubic, linear, quadratic, cubic, quartic, etc. And so they're really easy to take derivatives with. They're, for the most part, a lot easier to solve than, say, trig functions or other transcendentals. So we can use what's called a Taylor series approximation. And the idea here is that we approximate our chosen function around some point, right? So if you imagine, you're trying to approximate some periodic function, but instead of approximating the whole thing, what you're really aiming to do is, let's say you have some x value here, and maybe this is x equals 5. So in this case, this is our x naught. And what we aim to do is to approximate, what's going on right here in terms of some polynomials. Now, the reason polynomials work great is because, as you might remember, if you're taking a look at a constant function, a linear function, those don't have any changes in direction. When you get into a quadratic polynomial has one change in direction. So you get basically an increase and a decrease. You have two directions. And when you get into cubics, now not always, but you can write cubics to have two changes in direction. So here would be one change in direction going from increasing to decreasing, and then decreasing back to increasing. If you did a quartic, you could design the quartic to have three changes in directions, 1, 2, 3, and by doing that, you can see that we can start to approximate more and more the curvature of our actual function. And this is the Taylor series approximation formula. The derivation is not incredibly complicated. It's actually really neat. But the idea here is that you're applying the idea of rates of change, right? Because as you can imagine, derivatives tell us about how an output value is changing at a point, and then the derivative of the derivative tells us something about concavity, etc. But we can control by doing this. Now, if you notice, this first term here is a constant, and that is going to require us to evaluate our Taylor series function at x naught, and then the next term is what we call the linear term. If you notice what's going on here, you have x to the x minus x naught to the first. Now this x minus x naught, that's a shift. If you replace x with, say, x minus 5, it's going to shift your function 5 units to the right. So you can think of all of these x minus x naughts as basically shifting your polynomial over. So let's just say you're approximating this piece with a parabola. Well, if you use a parabola, then that parabola would normally be centered on the y-axis, but the x minus x naught will shift it over so that our polynomial actually approximates it right where we want on the curve. Now, this is called the linear term. It requires evaluating the first derivative at that point and then x minus whatever that point is. Then you get what's called the quadratic term. Quadratic term, notice, is 1 over, this is 2 factorial. Factorial means multiply all of the integers, starting at that integer all the way down to 1. So this would be 2 times 1. 3 factorial would be 3 times 2 times 1, etc. And so this is the second derivative evaluated at our point. This is the shift component. Notice it's a squared, so if you were to FOIL this out, you would get an x squared in here. So by using these first three terms, you're gonna create a second degree polynomial approximation, which is gonna be a quadratic. And then this cubic term here would give you, if you incorporated that as well, you get a third order approximation, or a cubic approximation. Now notice that this says equals, and this just says plus ... Well, in mathematical theory, you would need infinitely many terms in this equation in order to exactly equate the terms to the function f of x near x equals x naught. If we use a finite number of terms, well, depending on how many of those we use, if we only use the first two terms, the constant plus the linear, we get what's called a first order approximation. And notice that now we're saying that this is approximately equal, that our original function is approximated by this linear function. And then furthermore, if we did the second order, well, our approximation would get a little better, because notice it incorporates the first two terms, but also a third term which allows it to change directions. Well, now you get a second order or a quadratic fit. Let's take a look at how this works. It's a really neat process, and you'll be able to visualize exactly what I'm referring to here with this example. So let's say that what we want to do is we want to approximate sine of x. And here's a graph of sine of x between -4 and positive, x equals -4 and x equals +4. And let's say that what we want to do is we want to approximate this curve near x equals 2. So essentially what we want to do is we want to fit a polynomial that approximate within some small region of that point. Now, what we mean near that point and how closely our function will approximate this function and to what extent in terms of x values is really a matter of which function we're approximating. So in this case, it's sine of x, and we'll just take a look at how going through first, second, and third order Taylor series polynomials improves that fit. So that's what we want to do. We want to approximate it here at x equals 2. So to do the first order approximation, what we need is we're going to use f of x naught. Okay, so f of x naught in our case is 2. So what we would have is f of 2. So that would just approximate sine of 2 plus the derivative of sine, which is cosine of x, evaluated at our point. So in this case, it's going to be the derivative of sine of x is cosine of x, evaluated at x equals 2 would give us the cosine of 2. And that's going to multiply x minus x naught. Now, if you did some distribution here and you calculated this, then you would see that this is actually a perfectly linear function. In fact, if you do cosine 2, just make sure you are in the proper mode, which would be radians, and cosine of 2 would give you about negative 0.42. And if you distributed that negative 0.42, this is x minus x naught. We should just replace x naught with what it is, which is 2. Then we would get negative 0.42x. If you distributed that, negative 0.42 times negative 2 would give you negative 0.84. And then f of 2 would be sine of 2, and sine of 2 is about 0.91. So I'll just write it on the end here. And so all I want you to see is that, notice this is just a linear function, negative 0.42x plus 0.07. Negative 0.42x plus 0.07. So that's why we call it a first order, because it's just a linear function approximation. Let's take a look at what this actually does. So if I just go ahead and select this, now I've defined everything in here in terms of f of x, and I define this corresponding x naught, so I could just type in the general form of the function, and look at this. What we've done with this green line here is we have approximated sine of x near the point x equals 2. Well, I would say we did pretty good, but only if you really zoom in on that point. Well, now you can see that the green and the red are almost one and the same within some certain domain of x, right? You can see that if we go even as far as 1.992, which would be, this x value here, all the way to even 2.008, 8, you can see we do pretty good in approximating the red. It's hard to distinguish the two. And great, but it doesn't, right? It doesn't really fit the shape of it. We would want some sort of curvature to that. So maybe first order is not what we're looking for if we want to approximate some of that curvature. So how do we account for that? How do we resolve that? Well, we do the same thing for the second order, but we just add one more term to it. So in the second order approximation, it would be f of 2 plus f prime evaluated at 2. So that's still cosine at 2 times x minus 2. And now we would have plus 1 over 2 factorial, which is 1 over 2 times 1, which is 1/4. 1/4. Now the second derivative of, so if I write f of x is sine of x, then we know that f prime of x is cosine of x, and f double prime of x would be negative sine of x. So that's going to give us a negative term, a negative coefficient, negative 1/4, and this is going to be sine of x naught, which is sine of 2, multiplied by x minus 2 quantity squared. So there's our approximation now, and if you'll notice, this term, if you were to FOIL it out, you would get an x squared. So this would end up giving us a quadratic function. I'm not going to go ahead and multiply it out, but look at what you get. Now, that purple curve is exactly what we, oh, but it shouldn't be 1/4. I'm sorry, it should be 1/2 because it's 1 over 2 times 1. If I could maybe do some math, then that would be helpful. So this would be 1 over 2. And now you can see we get a much better approximation, right? In fact, not only do we get it near x equals 2, but one can maybe even argue that you can almost go a half unit in either direction, and you get a pretty good match of the purple to the red. Now, if you did a third order approximation, the pattern persists. Notice it's f of x naught plus f prime of x naught times x minus x naught. And then in our case, plus 1 over 2 factorial times the second derivative, which gives us the negative sine of 2 times x minus 2 squared. And now in the next term, we'll have 1 over 3 factorial. So that'll be 1 over 3 times 2 times 1, which is 6. The third derivative, which, by the way, sometimes instead of having to write all these hash marks, you just say f superscript parenthesis 3, close parenthesis, and that's the third derivative. It just makes it much more compact. And the third derivative will be negative cosine of x. And so in our case, this should be a minus 1/6 cosine of 2 times x minus 2 cubed. So that's going to give us our cubic term. And so now if we take minus 1, actually we could just do plus 1 over 6, because that should, the second derivative here, I'm doing it implicitly. Oh, no, but that's not right. That should still be 1/2, and then we get 1/6 over here. So watch what happens when I incorporate the third derivative in there and we do a third order fit. Well, let's just take off the purple one for a second and add this one, and you can actually see that it does pretty good. Now, it doesn't necessarily continue to expand your fit farther in other directions. It just does much better at its job near that point x equals 2. And you can see we get a pretty great fit for quite a while. And the more derivatives we add in here, the closer our approximation will be to our actual function sine of x. And that's where we set up here, that f of x is equal to the infinite expansion of such terms. So if you went ad infinitum, you can continue to do this, you would get a perfect fitting polynomial to your function. Oftentimes we stop at about third or fourth order because it's hard to do much better than that, but you could continue to do whatever order you want. Valuable tool when we're trying to approximate complicated functions with much simpler ones.